Hello, everybody. This is third lecture of chapter 8. And in this lecture, I'm going to go through Schrödinger equation and also name, shape, and radial distribution of different orbitals. And I start with this fact that electron has two nature or dual nature. One electron is a particle, and the second electron is a wave. Okay. And Schrödinger came with the equation that equation it will connect these two kind of like nature to each other. So we have an operator, we apply it in a function, and it will give us E and the function back. And E is energy. Through the Schrödinger equation, we get two answers. Okay, so we get two answers. First answer is energy of electron. And the second, volume that there is a chance to find electron in it. Okay, so there is a space or volume that we can find electron in it. Okay, and now what's this volume? Volume, we will call it orbital. And what's the orbital? Space or volume that there is a 90%. There's a 90% chance of finding electron. Okay, so 90% there is chance to find electron. Why not 100? What's happened with the 10%? I go with the Schrödinger experiment, Schrödinger cat experiment. So he said, let's assume you have cat, you have flask that it has poison in it. Okay, here, okay, so and one like, let's assume this one is our hammer. Okay, hammer, it has timer, and the container we can seal it by this cap. Okay, and this container is invisible, so we cannot see anything inside the box without lifting this cap. He said if you give it, let's say, give it 5 minutes or 1 hour, okay, give it 5 minutes or 1 hour, this timer, it will trigger, the hammer, it will kick the, the flask, and the poison gets out of the flask, and the cat will die. Okay, so if we give it, like enough time, logically, we expect that this one can happen and the cat will die. Okay? But there is no way for us to figure whether the cat is really dead or maybe by chance alive. So we can have two cases here. Dead cat versus alive. Okay, and this is really weird because there is no way to be dead and at the same time alive. And what's the problem with this one? What's the problem here with this experiment? Problem is here is that there is no way for us to figure whether it's dead or alive without ruining the experiment. And the way we ruin the experiment, we will open the box. So you want to know whether it's dead or alive, open the box. But the second you open the box, experiment is done. You stop the experiment. Okay, so we ruined the experiment, and that's a problem. Okay. The way we use this actually fact in chemistry, physics, or other science, we say there is no way for us, there is no way for us to find position of electron and energy of electron with high accuracy at the same time. So we are looking for energy of electron and position of electron. Okay. If you want to get both of them with high accuracy, that's not going to happen. That's not going to happen. I said, you want to know whether the cat is dead or alive, you have to open the cap. And then you will know for sure whether it's dead or alive. You want to know energy of the electron, you need to sacrifice something, and that's going to be position of electron. You want to know the exact position of the electron, then you have to close your eyes on the energy that you're going to calculate. That means you will have error in your calculation. Next thing is a Schrödinger equation that just looks really simple one. We can handle it or solve it only for hydrogen. Why hydrogen? Because hydrogen has only one electron. So you can handle the Schrödinger equation or solve the Schrödinger equation only for a system with just one electron. Okay, only one electron. And we know that sometimes we have more than one electron. So if we do have more than one electron, then there is no way for us to handle this equation. So we need to use approximation. But when we use approximation, that's the place that we are introducing error in our calculation. Again, we cannot solve the equation for system with two or more electrons. The way we handle it, we need to go with assumption. And if you use assumption, that means you are closing your eyes to some facts. So you will have error in your calculation. Okay, so maybe you heard this one in physics, that we have a law that we say uncertainty. There's no way to find position of electron with high accuracy and at the same time keep accuracy of the energy in really high level. That's not going to happen. You go with one of them. Okay, so now I said we're gonna deal with area that there is a chance to find electron in it, and we call it orbital. But in order to name any orbital, we need to have three quantum numbers. Okay, 3 quantum number for naming any orbital. Okay, first one we show it by N, second one call it L, and the third one we show it by ML. Okay. And N we call it principal quantum number. The second one, L, we call it angular quantum number, and the third one will be magnetic quantum number. So we need to have 3 quantum number to name any orbital. Like for human being, we used to use, first and last name. Sometimes we go with also mid name. And most of the time we have 2 names to name one individual. When it comes to orbitals, we need to have 3 of them. Okay, let's go through all of them and start with the principal quantum number. What's the principal quantum number? N. So I go with the first one, and it's N. Principal quantum number. Principal quantum number is equal to here 1, or start with 1, 2, 3, and goes up. And it will tell us distance of electron from nucleus. Okay, so distance of electron from nucleus. Okay, and here we have nucleus, or it has a proton, and this is first level of energy. Okay. That's going to be N1, R1. Now, when you increase N, you go to 2, you go here, nucleus, it has the protons, or you can show it by N. You have the first level of energy, or first layer, N1. Then you will have N2, showed by R2. Okay. So by increasing N, place that you need to look for to find the electron is going to be far from nucleus. Okay. So this is the place that I need to look for to find electron. That's the distance for it, R1, and that's R2. Okay. By moving from N1 to N2, distance that I need to look for it, R2, is going to be way far from nucleus, and it's going to be bigger than R1. Okay. So N is going to tell us how far we need to look for electron. How far from nucleus. Okay. Next one is going to be it's going to be angular quantum number. So I go with 2 angular quantum number. We show it by L. Okay, by L. L, it will tell us shape of orbital. Tell me the shape of the orbital. Is it spherical? Is it stretch? Square? You will know through the L. Okay. What are the possible answers for L? L is equal to 0 to n minus 1. And remember, n start with 1, 2, 3, and it will go up. N cannot be 0, because if n is equal to 0, that means we're talking about nucleus. If L equal 0, we call it S orbital. L equal 1, we call it P orbital. L equal 2, we call it D orbital. And L equal 3, we call it F orbital. Okay. And next quantum number, we go through ML, magnetic quantum number. Okay. Magnetic quantum number ML magnetic quantum number ML, it will tell us direction or orientation of orbital. Okay. And let's assume you figure, you know, like it's a stretch orbital, okay, or a stretch, you know, area that you need to look for it to find electron. Is it pointing this direction, up, or to the screen? Okay, out of screen in this case. Okay, so n is equal to 1, 2, 3, or up. L equal to 0, 2, n minus 1. ML is gonna be minus L, 2, 0, 2, plus L. So if n is equal to 2, ML is gonna be 0, 2, 2 minus 1. Possible answer will be 0 and 1. Okay, 0 and 1. We have two answers. What are the answers for ML? ML, you go with, if L equal 0, ML, it will be 0. If L equal 1, ML will be minus 1, 0, and plus 1. Okay, so that means you have three directions. Okay, three directions. Okay, so we said, again, I'm going to review whatever I said about orbitals. Go with this one. We said in order to name any orbital, we need to have three quantum numbers. We need to have n principal quantum number that's going to tell us distance of electron from nucleus. Okay. Distance of electron from nucleus. Next one is going to be L, angular quantum number. It will tell us, now that we know how far the electron from the nucleus, what's the shape of that area that electron is there. Okay, and the third one, ML, is going to be the magnetic quantum number. Okay, we know how far the electron is from the nucleus. We know what's the shape of the area that the electron in it. Now we need to figure, should we look horizontally, up, down, or another direction? So this one is going to tell us the direction of the orbital, or simple way, number of orbitals. Okay, and principal quantum number start with 1, cannot be 0, because if it's 0, then we're talking about nucleus. Okay, and it will tell us distance of electron from the nucleus, how far the electron is from nucleus. By increasing n, distance will be bigger. Second one, angular quantum number. It will tell us shape of orbital. L, it can be 0 to n minus 1. If L is 0, we call it S orbital. L1, we call it P. 2, we call it D. And L equal 3, we call it F orbital. The third quantum number that you need to use to name orbital is going to be magnetic quantum number. Magnetic quantum number is going to tell us number of orbitals or directions of orbitals. Okay. ML is equal to minus L, 0, 2 plus L. So minus L to 0, 2 plus L. Okay. And now I'm going to start with n equal 1, and I will show you how to draw all different orbitals that belong to n equal 1. Okay. So n is the principal quantum number. Okay. Another name that we use for it, level of energy. Okay. Level of energy. Okay. If n equal 1, what are the possible answer for L? L is going to be equal to 0 to n minus 1. And ML is minus L to 0 to plus L. Okay, let's use all the formulas that we have and calculate orbitals that we are dealing with. Okay, and 1, L is going to be 0 to 1 minus 1. So we have just one answer. L equal 0, we call it S orbital. This orbital belongs to first level of energy. First level of energy. So the way you will name it, you put level of energy first, and then you put name of orbital after it. Level of energy and 1, and then you say name of orbital, you go with S. S orbital is just one box. You can put 2 electrons in it. One is pointing up and the second is pointing down, and I will talk about why they are pointing up and down. Okay, what's the shape for it? Is it spherical? Okay, it's spherical. The question is, why is it spherical? Let's calculate ML. ML, put L equal 0, it's going to be just 0. You have only one direction. Only one direction. Okay, so anyway you reach the orbital, you're going to deal with the same thing. And the only way I can actually present this sentence or have sentence is to draw a sphere, and anyway from anywhere you reach this sphere, you will see the same surface. So reason we draw s orbital as a sphere because we have only one direction. Okay, only one direction or only one orbital. Okay, here is the nucleus. Okay, for now, you put positive sign in it, and I will talk about this one. Y is positive. Okay, so n equal 1, n equal 2. Possible answer for L, 0 to n minus 1. So it will be 0 to 2 minus 1. That means you get 0 and 1. Okay. If it's 0, we call it S. If it's 1, we call it p orbital. Okay. So I have two orbitals, S and p. Okay. Forgot to add something. Here we said n we call the principal quantum number, level of energy. Also we call it shell. Okay, we call it shell. Okay, so now when n is equal to, I have L equal 0 and 1. L equal 0 is a s orbital, L equal 1 is a p orbital. Okay, so we have two cases. First case, n equal 2, L equal 0. So ML is going to be just 0. Because it's 0, we have only one orbital. Only one direction. And I'm going to show it by sphere. Okay. This is the nucleus. Let's call this one n equal 1. Then that one is going to be n equal 2. Okay. And you go positive. That one it will be negative. Okay. Positive, negative. Okay. So the first one is positive and outer one is negative. Okay. Again, I'm going to mention how to sign, the positive and negative. So second case, n equal 2, L equal 1, and then ML it will be minus 1, 0, 2, plus 1. Okay, let's name this orbital. We said we start with n and then name of the orbital. You go with n and name of orbital. N is equal to, name of orbital is S, so it's 2s. 2s is one box and it can accommodate 2 electrons. Okay. Next, n equal 2. Sorry, n equal 2, my bad. N equal 2, L equal 1, and possible answer for ML, it will be minus L, 0, and plus L. So ML, it will be minus 1, 2, 0, 2, plus 1. Okay, this time we have 3 orbitals. We have 3 orbitals. And this is L equal 1, we call it P orbital. Okay. We have 3 orbitals that all are p orbitals. Here's the p orbital. You draw two lobes. You give one positive, second negative. Let's say this one aligned with the z. You say this is p orbital that align with the z, so you say is pz. Okay. Assume this is y. Then it will be plus, minus, we call it py. And if this one is x, this one it will be px. So for n equal 2, L equal 1, we have three directions here, three orbitals, because we got three answers for ML. All of them belong to p. So p orbital is going to be made of three orbitals or three boxes, and each box is going to accommodate 2 electrons. So we can have 6 electrons. What's the name for them? I go px, here px, py, pz. Okay. Is there any connection between -1 and x, 0, y, and +1 and z? No. There is no connection really between them. You can call this one y, call this one x, call this one z, or whatever. I need to use three x's to name these three orbitals. That's it. Okay. So now before I start n, I'm going to show you how to get these signs. And then I will talk about node. We'll have subject, name of node. What's a node? Node, at the beginning of this lecture, we said Schrödinger managed to come with equation that is connect particle nature to wave nature. So electron, it can be a wave. Okay, if electron is wave, then draw a wave. We said distance between two identical points, call it lambda, show it by m, and distance between the horizontal line and the maximum point, we call it amplitude. Okay. Now, wherever this wave hit the horizontal line, here, there, or there, we say the probability of finding electron is going to be 0. Or, okay, sign of the wave, it will be different one. From positive, it will turn to negative. Sign of the wave, it will turn from positive to negative. Positive, then it goes negative. Okay. So node is a place that function go through 0, or it will change sign. Okay, so this is node. Okay, we show this one here, we call this one function. Side 2, we call it probability. in node psi 2, or probability is going to be equal to 0. There is no chance to find electron there. So when we have a node, anywhere we have a node, we say there is a 0 chance to find electron in it. Okay. Again, node is any place, anywhere, any like a surface, or any point that the wave it will change sign, or there is a 0 chance to find electron there. We have two types of nodes. Total nodes equal to n minus 1. Okay. And n minus 1, which is total, you can break it to two parts. You go with angular node, and the next one is going to be the radial node. Angular node is going to be a flat plane. Okay. So one flat surface. Radial node, it will be a circle. Now, angular node is equal to L. Okay. Angular node is equal to L. The total is n minus 1. So you say n minus 1 is the total. And if I use L from it, whatever left is going to be radial. So radial is going to be the total n minus 1 minus whatever we use for the angular. That's going to be the radial. So angular node is going to be equal to L, and radial node total minus L. Okay, now let's go back to orbital that I showed you. And I start with s orbital, 1s orbital. Okay, 1s orbital, I draw a circle, and then I put the nucleus, and it said plus plus. Okay, let's talk about 1s. N equal 1. Total node is going to be n minus 1. It will be 1 minus 1, 0. We don't have any node. Okay. What's the possible answer for L? It's going to be 0 to n minus 1. So it's going to be just S. Just S orbital. How about ML minus L 2 plus 2, 0, 2 plus L. We have L equal 0, only only 0. That means we have one direction. We show the nucleus that it has the protons in it. Okay. Now you look to total node. Do I have any node? No. Okay, I don't have any node. So you start with positive sign. You put positive sign anywhere. Okay. This is orbital that belongs to first layer, and name of the orbital is S. Okay. Next, you draw this. You say distance from nucleus here is psi 2 or probability. Okay, so this one is psi 2, or I'm going to say radial probability. Radial probability. I want to know when I move out of the nucleus radially. Okay, radially. So you have to find the center and move out. Okay, radial. Do not cross the entire orbital, okay, because it says radial distribution. Okay, radial distribution. So I want to know what's the chance of finding electron. How does chance changing? Is it gonna go up or down? From nucleus, there is 0 chance to find electron. Psi 2 or probability is going to be equal to 0. When I move out of the nucleus, it will go up. And then it will go down. This is nucleus, so the starting is the nucleus. This is here, end of orbital. That's maximum point is telling us that if we are looking for an electron, we should search this distance. We should search this distance to find the electron. We have the highest probability or chance to find it in this R. Okay. We call this graph, we call it a radial distribution graph. Radial distribution graph. Okay. Next, go n equal 2. Okay. If n is equal to, possible answer for L, it will be 0 and 1. We said this is S, and L equal 1. We call it p orbital. Case 1. N equal 2, L equal 0, ML equal 0. Okay. How about the total node? Total node, we say it's going to be equal to n minus 1. N is equal to, so 2 minus 1, 1. This time we have a node. We have a node. First case, n equal 2, L equal 0, ML equal 0. Okay. And we have one node. Okay. Angular node equal to L. And because L equals 0, we don't have a plane or flat node. Radial node is going to be n minus 1 minus L. Whatever left. 2 minus 1 minus 0, 1. So we have one circle node. Okay. Draw the s orbital. S orbital here is equal to, sorry, I have to show the nucleus first. This is the nucleus, n equal 2. We have one node, and I'm going to show it by a circle or dot. This is radial node. Okay. Radial node is the place that is going to change sign of the wave, or there is a zero chance to find electron in it. So you start with a positive sign. You cross the node, you will make it negative. Okay. Now draw a radial distribution graph. You show the psi2 or probability, psi2 or probability versus this one is going to be distance from nucleus, and radially move out of the nucleus. When you move out, you will get a chance to find electron until we reach this node, first node. Then when we cross the node, we get a bigger area. We show it by a bigger peak. This one is the node. Okay, so this is the node. We have one node here, there's zero chance to find it, and this is the node. Again, we call this a graph, radial distribution graph. Second case, n equal 2, L equal 1. So we go n equal 2, L equal 1, ml minus 1, 0 plus 1. And this is going to be p orbital. Okay. How about the total node? N minus 1, 2 minus 1, just one node. Okay. Angular node, it's going to be equal to L, and this time L is equal to 1. So we have a plane node. Radial, it will be 0. N minus 1 minus L, 2 minus 1 minus 1, 0. We don't have any circle node or radial node. Okay, draw the p orbital. Here is a p orbital. Show the nodes, any node you have. I have only radial node. A radial node, it will chop the orbital to two identical half, and it's going to be perpendicular to the orbital. Okay. This is the angular node. Start with any sign, whether it's positive or negative. It doesn't matter in this case. It doesn't matter. Let's say you go with negative. Again, it doesn't matter, negative or positive. When you cross the node, you will change it to positive. Okay. Show the radial distribution graph. You want to know when you move radially out of this orbital. Okay, this is the nucleus. Okay, center of any orbital is nucleus. There is zero chance to find electron there. Psi2 is equal to 0. Okay, so all nodes are going to pass, the nucleus. I'm talking about angular nodes. Angular, not the radial nodes. So psi2 versus r, or distance from nucleus. From the nucleus, move out radially, okay? Radially. They're up or down, it doesn't matter, but only one direction, either up or down. Okay, so from nucleus, I move up. Now I have a higher chance to find electron. And then when I reach here, this is going to be the end of orbital. End of orbital. Okay. This is radial distribution graph for 2p orbital. You might you might actually come with this question that when we draw the radial distribution graph for 2s orbital, we show the second area bigger than the first one. Okay. And I want to say why I draw the second one bigger than the first one. Because I will be dealing with it when I go to orbitals belong to n equal 3 or 4. Okay. You draw a circle and cut this part from the circle. So I'm gonna chop this part. Okay. Next thing is divide it. I divided by the radial node. Area number 1, area number 2. Okay. Area number 2 is bigger than area number 1. So when you draw the radial distribution graph, you say psi 2 versus r, you want to follow this basic math rule that A1 is smaller than A2. So show it in your graph that A1 is smaller than A2. This is area number 1. And that's area number 2. Okay. The outer area is bigger than inner one. And that was the reason that I drew the second peak bigger than the first one. Always you will follow this pattern. It doesn't matter how many peaks you have. The last one is going to be the biggest. Okay? Last one is going to be biggest. And remember, this is nucleus. This is the last one is going to be end of orbital. So you cross the horizontal line only one point, and that's going to be, this one is going to be the node. And your node is radial node. Because you cross it only one. You cover initial and the last point, and now you check the graph, and as you see, we cross the horizontal line only just one time. So we say we have one radial node. Okay. Now let's talk about n equal 3, and I will finish the chapter with n equal 3. N equal 3. What are the possible answer for L? L is going to be 0 to n minus 1. So we will have L equal to 0 to 3 minus 1. We get 0, 1, and 2. 0 we call it S, 1 we call it P, and 2 we call it D orbital. So first case, n equal 3, L equal 0, ML is going to be equal to 0. How about the total node? N minus 1, 3 minus 1, we have 2. Angular node equal to L is going to be 0. So radial node is going to be equal to 2. Here's the s orbital. We have, let's show the nucleus. We have 2 radial nodes. This is the first one. That's going to be the second node. Give it sign. I go positive, negative, positive, negative, positive. Show the radial distribution graph. Radially, from the nucleus, move out, not, do not cross the diameter. Okay, so when we move out, we have area number 1, area number 2, and this one is area number 3. So we will have 3 areas. One area, second area, 3 areas. So we have 3 areas. We need to show 3 areas. Okay. 2 times we cross the horizontal line. That means we have 2 radial nodes. And this is psi 2 versus r. This is radial distribution graph for orbital that's belong to the 3rd layer. And the name is S. You can accommodate 2 electrons in it. Okay. Second case, n equal 3, L equal 1. So the second case, n equal 3, L equal 1, ML is going to be -1, 0, and +1. This is p orbital. Total node n -1, 3 -1, 2. Angular node is equal to L, and L is 1. So we do have 1 plane node. Radial node is going to be the total minus angular. It will be 1. So you have 1 circle also. Draw the p orbital. Here is the p orbital. Show all the nodes. You will have 1 angular node. And also we have 1 radial node. From the nucleus, I will move radially and I will chop this orbital. Give it, say, negative. I go positive, negative, positive. This is the nucleus, remember. Show the radial distribution graph. Okay, move either up or down. I move out, here up. I see 2 areas. The outer is bigger. First, that's the second. Okay, radially move out, and only in one direction, not both directions. You can go either up or down. Probability of finding electron versus distance from nucleus. And what's the name of the orbital? Is belong to the 3rd layer, and is a p orbital made of 3 boxes. It can accommodate 6 electrons. Okay, call them 3px, 3py, 3pz. And the last case, n equal 3, L equal 2. So now we will be talking about d orbital. Third one, n equal 3, L equal 2. Possible answer for ML minus L to 0 to plus L. So ML will be -2, -1, 0, +1, and 2. So we have 5 directions. That means 5 orbitals. 5 orbitals. Okay. How about the total node is going to be n-1. Be n-1. So we're talking 3 minus 1. We have 2 nodes. Angular node equal to L, and L equal to radial node total minus angular. 3 minus 1 minus 2, 0. So we have only angular node. Okay, now we need to show the d orbital, and we have 5 of them. So before I draw the shape of orbital and show the sign, I need to show you how to get a d orbital, how to draw a d orbital. We need to have 5 of them. You go with this. Draw plane. Name this plane, give it here. I go with X and Y. And I put 2 lobes there. Okay. I call this one d orbital that's belong to XY or dyx plane. Okay. Now I said I have 2 angular nodes. Radial I do not have. So show the 2 angular nodes. You will put 1 angular node here. And the second angular node, you put it there. Okay. Now give it sign. I go with negative, and I will mirror it. Do not go cross. Okay, do not go cross. Either this direction or that direction. Mirror, not perpendicular. The angular nodes are not perpendicular, so you don't have the right to go cross. Just mirror it. You mirror it, it will be plus. You mirror it here, it will be negative. You mirror it there, it will be plus. Next orbital, I go with, keep this one X, and I'm going to call this one Z. Okay, I have 2 angular nodes. First one, I will put it there. And the second one, I will put it here. Okay, so angular node. This one also angular node. I go with negative. This one will be positive, negative, positive. What's the name of this orbital? Is d x z equal to d y z. So we got 2 out of 5 now. Third one. We go with let's this time call this one Y and call this one Z. Show the nodes again. I got negative, positive, negative, positive. What's the name for it? It will be dzy equal to dyz. So out of 5, okay, out of 5 orbitals, I showed you 3 of them. I need 2 more. I need 2 more. And I go with this. Go y. So this one is y and this one is x. This time I will put the lobe exactly here. Okay. And I will put the mirror, the angular node there. These are going to be the angular node. Start with any sign. Let's say we decided to go with positive. Positive here, you mirror it, it will be negative. You mirror it there, it will be positive. You mirror it there, it will be negative. Okay. Now, what's the name of the plane? Name of the plane is XY. We cannot call it dxy or yx. Why? Because we already used the d. Why this one is z? Sorry about this one. It's a dx, my bad. Sorry about this one, guys. This is the dyx. Okay, I think shame on me, guys. Like, sorry about this one. First one is dxy or dyx. Here dxz or d or dz, dzx. Okay, shame on me. Sorry about this one, guys. So simply the way you name it, you say the plane is xy, so it will be dxy or yx. Plane is xz or zx. Plane is yz or zy. Okay. Is it 3:04 a.m. and I think my brain is going down. Okay. This time I can go with x, y because I already used it. And the way I'm going to show that this is belong to xy plane, I go with dx square minus y square. That's the the 4th orbital. And the last orbital, this is z axis. You draw almost a p orbital. You put a positive sign for it. And you draw loop around it. And you put negative sign inside this loop. We say this orbital is a d orbital that lined with the z, so we say dz square. So we have 5d orbital, dxy, dxz, and dyz, dx square minus y square, and dz square. So now we have 5 orbitals. because we have 5 orbitals, the d orbital is going to be d orbital. It's going to be orbital with 5 boxes. It can accommodate 10 electrons. Okay, let's choose any d orbital. This is gonna be Y, and that one is X. We said we have nodes, 2 angular nodes. Angular node, we go negative, this one will be positive, negative, positive. Now draw the radial distribution graph for it. Sine 2 versus R. From the nucleus, this is the nucleus. From the nucleus, move out in one direction. Choose any one, any of these lobes. I'm gonna go in this direction. I see only one area, just one area. Hold this one, treat it just one area. Here is just one area. This is radial distribution of a d orbital. So I'm gonna say I'm dealing with an orbital that belongs to the third layer. I call it the 3D orbital. Okay. So I showed you orbital of N1, N2, N3, and how to get the nodes for them, how to show the, or draw the orbitals, and also radial distribution graph for them. Now, from n equal 1, we have only one s. We can accommodate 2 electrons in it. N equal 2, we'll have 2s, and also 2p. N equal 3, said we will have 3s, then 3p, then we will get the 3D. And the 3D, I'm going to draw it here. I need more space for 3D. We can put 10 electrons in it. Okay. Okay. So as you see, when we go up in n, when n is going up, we are adding one new orbital. N1, we have only one orbital, 1s. N2, we have s and p. So now we have 2 orbitals. The new orbital is going to be the 2p. And we go to n equal 3. N equal 3, we have the s, we have the p, and the new orbital now is a d orbital. If you go to n equal 4, we will have 4s, 4p, 4d, and 4f. The new orbital, it will be f orbital. So as you see, like every time we are adding new orbital. Okay. In first level of energy, or first shell, we can accommodate 2 electrons. Second shell, we can accommodate 2 plus 6, 8 electrons. Third shell can accommodate 2, 6, and 10, 18 electrons. And we call the principal quantum number or level of energy, or shell. L, we call it sub level or sub shell. Sub level or sub shell. So if you see those stuff in a shell or sub shell, don't be surprised. Okay. In your slides, I put more examples about this orbital 5p, 4s, and also I said like this is for, this is a p orbital. Draw the radial distribution graph for it. This is d orbital, so show me the cartoon for it. And I'm gonna practice all of them for you. Okay, it's a p orbital because it's a p orbital. L equal 1. N is equal 5 because n equal 5. So it's a, here you say is a 5p, 5p, n equal 5, and because it's a p orbital, for p orbital, L is going to be equal to 1. Angular node is equal to L, so that's going to be 1. Total nodes, you go with n minus 1, 5 minus 1, 4. Out of these 4, you're going to use 1 for radial. So you say out of these 4, sorry, 1 for angular. For angular node, it's going to be equal L, it's going to be 1. So what? 1 out of 4, you will have 3 radial nodes. It's a p orbital. Okay. Here is the p orbital. You have one angular node, and we have 3 radial nodes. 1, 2, 3. 3 angular nodes. 3 radial nodes, sorry, 3 radial. Node. Give a sign. I go negative, positive, negative, positive. How many areas do we have? 1, 2, 3, 4. We have 4 areas. So we need to show 4 bonds. 1, 2, as you move to the right side, you increase the size of the areas. 2, 1, 2, 3, 4. 4 areas. Okay. This is radial distribution graph of 5p orbital. Next, they gave you 4s, L equal 0, N equal 4. So 4s, N equal 4, L for s orbital is going to be equal to 0. Okay, so angular node equal to L equal to 0. Total node n minus 1, 4 minus 1. You have 3 nodes. All of them, they will be radial because the angular is 0. Is the s orbital. We have 3 angular radial nodes here. 1, 2, 3. Negative, say positive, negative, positive. Side 2 versus R2, we have 1, 2, 3, 4 areas. I will draw 4 areas, and as I move to the right side and increase the right side and increase the size of the areas or size of the bomb. 1, 2, 3, 4. This is 4s orbital. Let's show you the radial distribution graph for 4p orbital and also the animation here for it. Now I go through 4d orbital. So we have 4d n equal to 4. L for d orbital is equal to 2. Total node n minus 1, 4 minus 1, 3. Angular node equal to L equal to 2. Radial is going to be 3 minus 2, 1. Or n minus 1 minus L. 4 minus 1 minus 2, 1. Okay, is that d orbital? Okay, this is d orbital. Show the angular nodes. Here is one angular node. And that's a second angular node. We have one radial node. Okay. Now, give it sign. I go with negative. Okay. You want to make it positive? Here, positive. It doesn't matter. So if this one is positive, when you cross the node, it will be negative. Now, either go up, here, sorry, down, or to the left side. I will mirror it, it will be negative. Here it will be positive. You mirror it, positive, negative. Mirror it, negative, positive. Okay. Now, radially, from the nucleus, move out and only in one direction. So I'm going to move this direction. I see 2 areas. And then, so I'm going to show 2 bombs. 1, 2 areas. Remember, this is the first area, area number 1, and that's going to be area number 2. So we have 2 areas. Area number 1, area number 2. And this is the radial distribution graph for 4d orbital. And by this one, I'm done with chapter 8. Hope this lecture was useful, and sorry for the typo that I had when it was when I was talking about name of d orbitons. Have a great weekend, guys. Take care.